Hello everybody. In this video we're going to discuss the difference between two units that are kind of similar or might be confusing if the difference is not very clear. So this is what I want to discuss here, which is the difference between separator and splitter. To demonstrate the difference, we have these two diagrams, one to the left here where we have a separator, we have one stream in and two streams out, and the same here for the diagram to the right, we have one feed in and two product streams. We have the same three components in the three streams, the same three components in the three streams. So there is some difference between these two units, although they appear to be almost identical. And this difference is very, very important, and it has very big impact on how we can do the calculations for both, which is a consequence of the function of each of them. So the separator is a unit that we discussed more than once before, and we said that separator is a unit that is used to separate the components. So we have A, B, and C, so we can produce two streams by using this separator, which can be a flash drum, can be a distillation column, can be any other separation unit. And the streams, the top stream, let's say if it's a distillation column, then it will be reached in A, and the bottom product would be reached in C. So the composition here is different from the composition here, is different from the composition here. So the composition in each of one of these streams is different. And this is the main function of a separator, is to separate the components. So by definition, a separator will change the compositions of the components in the three streams. So this is the first thing, or the separator. So by definition, again, the separator will have the mole fractions in stream 1, 2, and 3 would be different for the three components. On the other side, when we look at the splitter is just something that splits the stream, meaning that we have a stream that has a flow rate, let's say, of 100 kilograms per hour or 100 kilomoles per hour. This splitter can be just a T connection. You know, the T connection is if you have a pipe, and this pipe can go into a connection that looks like this. So part of the flow will go to this side and part will go to that side. So it's just splits the flow. So this is the same thing. It can be a T connection, can be some other thing depending on how the shape looks like. But at the end of the day, the splitter will just split the flow. So if you have the 100 kilomoles per hour, you can have 30 here and 70 here, you can have 40 here and 60 here, but the splitter will have no effect, and this is the main point of the splitter that must be clear. That splitter has no effect on the compositions. So if we have a splitter, then by definition, the mole fraction of A in stream 1 is equal to the mole fraction of A in stream 2 and stream 3. The same for B and the same for C. So this is the main function of the splitter, is to just splits the flow. It has no contribution to changing the compositions. So this is the very big difference between the separator and the splitter. And according to this, we will have to take into account that we have similar compositions when we do the degrees of freedom analysis and when we do the mass balance calculations. And this is what we are going to discuss in the coming slides. So let's say we have this splitter here. We know the feed flow rate, 100 moles per hour, and we have the compositions of two components. And of course, the third is going to be known, which is 1 minus 0.2 and minus 0.35. And we know that the splitter is splitting the flow into 4 splits. So it's you have 4 different streams coming from the splitter. One of them, we don't know the flow rate of the first, but we know the flow rate of the second is 25. The third is 15. The fourth is 20 moles per hour. And we want to perform the degrees of freedom analysis on the splitter. And if we do the degrees of freedom analysis, again, we have the number of variables, number of given variables, the equations, and additional relations. So if we try to calculate the degrees of freedom by counting each one of them, the number of variables, we have 5 streams. Each one of them contains 3 components. We have 15 variables. The number of given variables that we have are 1, 2, 3, 4, 5, 6. So we have 6 given variables. We have 3 components, so we can write 3 independent balance equations, and we have no additional relations up till now. So if we calculate the degrees of freedom, we will find out it is 6, which means that I need 6 extra information to do the mass balance on the splitter and calculate the missing information. However, if you keep in mind that the splitter doesn't change the compositions, then we know that the mole fractions in this stream are the same as the mole fractions in the 4 output streams. So we know all the compositions in the output streams. So the only missing variable that we want to calculate is N2, and N2 can be calculated by simple balance doing the total balance on the splitter. So we say that 100 equals N2 plus 25 plus 15 plus 20. So this makes the N2 40 moles per hour. So it's solvable, although the degrees of freedom is saying that it's not solvable. Okay, so there is something that we need to understand now, that there is something wrong with the degrees of freedom analysis, because the main function of the degrees of freedom analysis is to tell if we can solve this unit or we cannot. And given the information that we know and the function of the splitter, we are able to solve the unit. But the degrees of freedom is not saying this. The degrees of freedom is telling us that we need more information. So the main issue that we have here is that we are not taking these compositions, or these equal compositions, we are not taking the equal compositions into account when we do the degrees of freedom analysis. There must be something here in one of these terms, especially the equations and additional relation, that will say that we have the number of components or the compositions are equal in all the streams. And since this is not there, degrees of freedom is not recognizing this fact, so it's saying that we have under a specified unit. So to take this into account, we can add what we can call a splitter restriction. So this is an additional relation. So it's kind of built-in additional relation. So this additional relation is a number that we put in the degrees of freedom analysis, and this number adjusts this difference in the degrees of freedom. So it takes into account that the compositions are equal, and it's calculated as follows: as number of components minus 1 multiplied by number of splits minus 1. So we have 3 components and we have 4 splits, so it's going to be 3 minus 1 times 4 minus 1 equals 6. And now when we do the degrees of freedom analysis, we add this built-in additional relation, which is the split restriction, and the degrees of freedom is 0. So it's as simple as this. And the good thing about the split restriction is that we don't do anything different for the degrees of freedom calculations of the splitter. We calculate the number of variables the same way, number of given variables the same way, number of equations the same way. We only you just need to be aware that this is a splitter and put the splitter restriction as an additional relation. And that's it. So this is the solution to the problem. When we do the solution, we will say that YA1 equals YA2 equals YA3 and YA4. So we will put the numbers. So this is what we can do. There is one other suggestion, or it's a question that will jump into your mind, which is, okay, since we already know that the compositions are equal, why don't we just put the compositions in all the streams and deal with them as given variables? Which is a very, very, very valid question. So this is what we have here in this diagram. So in the previous case, we had only the given variables or the given compositions were in this stream, while the knowledge of the splitter tells us that the composition here is the same as all the rest of the streams. which is right. We cannot claim that this is wrong. So this is one other option, but I want to go into more details regarding this solution. So let's compare the degrees of freedom for the case 1 and case 2. So case 1, we add the splitter restriction here as an additional relation, and the degrees of freedom is 0. However, for the other case, we have still 15 variables. 3 times 5, we have 5 components, 5 streams, each contains 3 components, so you have 15 variables. The number of given variables, let's count the number of given variables here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have 14 independent given variables and 3 equations. This gives us a degrees of freedom of -2. So one of them is not right. So we cannot have different degrees of freedom for the same unit. So why is one of them, or why are they different? They're different. So it has to be 0. And the problem actually lies in the way we calculated the degrees of freedom here regarding the number of equations. So to understand this, let's write down the equations that we have. So we are saying here in the degrees of freedom that we can write 3 independent equations, which is what we do all the time. So if you look at the equations that we can write the total balance, which is n1 equals n2 plus 3 plus 4 plus 5. Okay. If you do the balance on A, it's going to be A in stream 1 equals A in stream 2 and 3, 4, and 5, which is the mole fraction of A in stream 1 times the molar flow rate of stream 1, and the same for the other streams. And the same for component B. If you look at the equations, you would see that there is some interesting thing here. The second and third equations are actually the same as the first equation multiplied by a factor. So if you multiply the first equation by 0.2, we get the second equation. If you multiply the first equation by 0.35, it gives us the third equation. So the 3 equations that we claim are independent equations are actually not independent. They are dependent. We have only 1 independent equation and 2 dependent equations. So the splitter, again, this is because this is the nature of the splitter, can be described only by 1 independent balance equation. So let's update what we have regarding the degrees of freedom. If you want to include the components in all the streams, it's fine, but keep in mind that you have to write the number of equations equal to 1. So comparing, so this makes the output the same for the 2 cases. So comparing the two approaches that we have the first approach where we calculate everything the same, the number of variables, the number of given variables. We don't add any extra information on the rest of the streams. The number of equations is calculated the same way, but we add the number of additional relations. So this is the only difference here, which is the additional relation for the splitter. This approach. The second approach, we have to first put the compositions in all the streams, which is one extra step that you will do. The second, that you have to keep in mind that the number of equations have to be 1. You have to write the number of equations equal to 1, and we don't add any additional relations. So these are two possible options. It's up to you. If you want to go for the first option, it's fine. If you want to go to the second option, it's fine, as long as you are doing it correctly. I have a preference myself, which is something that I really encourage you to do. Again, it's up to you, but this is, let's put it this way, it's my personal preference, is to go for the first approach for 2 reasons. The first is, if you have a big flow sheet and you have many units, there is a very big probability that you will forget about putting the number of equations equal to 1, and forget about putting the components and the rest of the streams. So you have to do some extra effort to make sure that this approach is done correctly. The second, which is the most important point in my opinion, is that this approach is not valid for all the cases. Meaning, if you have a splitter in a big flow sheet, and this splitter contains 4 components, 3 components, and it has different splits, but we don't know the composition of any of the streams. And let's say you have a splitter like this, and you don't know the composition in the feed stream, and consequently you don't know the compositions in all the streams. So you cannot do this. You cannot put the compositions in all the streams because you don't know any of them. So we agreed that we do the degrees of freedom in the very beginning before we even start solving or performing the mass balance calculation. So in the beginning, while you have no given composition in the splitter, there is no way you can include the fact that the compositions in all the streams are equal using this approach. So for the degrees of freedom analysis, you'll be stuck in a way or another, because you don't know how to put this in the degrees of freedom analysis. However, here it doesn't matter. You know this composition, you don't know it doesn't matter. You just put the split restriction, and it is you are done with the degrees of freedom analysis. So this is what I prefer. Again, it's your call. It's totally up to you. As long as you are doing the degrees of freedom analysis correctly, it's fine. So this is all for this video. Next video we will be solving one problem just to practice more this splitter degrees of freedom thing. So I'll see you next time, John. Goodbye.